flicked to the slide yesterday about relative motion. So yesterday we touched on two topics, right? We did inertial and non-inertial frames of reference, so how you see something happening. And then relative motion is measuring motion based on your frame of reference. So if you have different frames of reference for viewing different things, like in this picture here, right, you have the everybody, or all those little speech bubbles are all based on this hood ornament here. So they all have different viewpoints of how that hood ornament is moving on that car, right? So we don't have hood ornaments anymore, but so you have this one, the red car says 0 kilometers an hour because they're moving in uniform motion with the hood ornament. The Corvette over here is going towards the red car. They have the same speed, so he's saying that the hood ornament's coming towards him at 110 miles per hour, right, because the two speeds kind of going together. And then we have the person here who's watching the hood ornament go to the right at that specific time. And then the green car down here is at right angles to it, so it's a Pythagorean theorem type problem that's going to change. Does that make sense? So, okay. I'm going to show you this video first, and then we'll talk about it. Because one of the things I find students have a tough time kind of visualizing is what relative motion actually is. So when you see a diagram like this in your textbook or anywhere, sometimes I know students see that the plane is literally flying this way, but the wind blows them back this way. So they look at it as two different things happening at separate times, as opposed to what it actually looks like as your ground speed down here. So I don't know if you've seen this video before last year. This is from the Bristol Airport in the UK. So this is just a stormy day, and what I wanted to show you in this video was what relative motion looks like. And let me get it up and bigger so you can see it. So here comes the plane towards the runway. As you can see, it's not super exciting. But what you don't know is that the plane, because the winds are so bad as it's approaching the airport, the plane is actually flying this way. But it has to point itself somewhat into the wind to counteract the wind. So it has a component into the wind and a component towards the runway. So you can see it more here because it's not pointing down the runway at all. And then just as it gets the runway, it's quickly got to reorient itself to get so it's driving straight down the runway. How scary would that be if you're on that plane and you see this runway coming up out your window? And as you it's called crab walking. So I'll replay that just so you guys can see the end part.
I'm never going to be a pilot. But I mean, respect to the pilot, though. Mm-hmm.
Right, so when we talk about relative velocity again, right, we have the velocity of the wind on the plane, which is pointing it one way. We have the velocity of the plane in the air, which is pointing into the wind and towards the runway. And then the resultant vector is towards the runway. So if we call the wind the x direction and towards the runway the y direction, the x directions kind of cancel each other out and you're left with the y direction. So if we go back to what I had on my slides, right, so we had the plane, right, is going towards the runway and into the wind. We have the wind pushing it back. So the resultant velocity is straight towards the runway. So however much the wind's push or the plane's pushing up, the wind pushes down with the same amount, so they cancel each other out. And it just keeps on going straight. I don't know if that helps you out or not, but that's kind of what's going on. And if you've ever gone like boating in some regard, like canoeing or swimming in a fast river, right, that's also relative motion because your body, right, you orient yourself depending on what your goal is, right? It was to get directly to the other side, you have to swim a little bit upstream and across the water to get directly across to the other side. But if you face your body directly at the other side, the water will push you downstream so you don't land where you want to land, right? So your body, you can kind of figure it out. If you play golf or any sport outside, right, you think about that when you have wind, right? If you have to kick a ball into the wind in soccer or hit a golf ball and the wind's going across the fairway, right? You have to hit it into the wind. So whatever speed you hit, you launch the ball at, it counteracts the wind so it goes where you want it to go. Right? So there's lots of different things as examples of it. And then I think last year you did like linear stuff with relative motion, if I'm not wrong. And you would have talked about maybe how, like, going back to airplanes, right? Airplanes always land going into the wind because it makes the air fly faster over their wings, which allows the plane to go slower towards the runway. It makes the landing safer, right? So there's lots of examples of relative motion. On this slide here, I wanted to make sure that you knew the two parts here. One, grab my markers over here. The first thing is that when you do these problems, you're dealing with vectors. It's the same as you do in math class. You're dealing with vectors. They're all speeds, so they all have little subscripts beside them, and that might be different than math class. But when you do it, when I say that the vectors, the order of the vectors is important. If I write this, which is this vector up here, right? I had to write down VPG is equal to VPA plus VAG. So I would write the vectors down in that order. And the reason why that's the quote-unquote correct order is that it kind of forms a chain. So you have if this is the vector, the resultant vector on the outside, which starts with the letter P, then the chain starts with the letter P. Inside the chain, if A is the last one in one vector, it needs to be the first one in the next vector. So it kind of links together, so you know which way you're adding them. And then whatever your chain is, if the last letter in your chain, in this case, is G, it should be the last letter in your resultant vector over here. It's just more of a communication thing that you know how the vectors are added together when you do them. But we also know that if you add two vectors together, the order doesn't really matter because you still get the same resultant. This is kind of like a physics thing, which is a little weird. And that brings me to the second part here, is that when you do your vectors, you have to define your variables because they're all velocities. So unlike anything we've done so far, right, where the variables are all different, right? Acceleration's A, velocity is V type stuff. Bless you. In this case here, because they're all velocities, right, you have to tell me what do you mean by VPG, right? So in this case here, we know that the VPG, we want to keep it simple. We can write VPG equals the velocity of the plane relative to the ground. So I have P and G, right? Plane relative to the ground. So you're defining what the frame of reference is for that measurement, right? That's where this frame of reference business comes in. So on your test, you usually get marked for defining your variables. So just make sure you do that extra step. Sometimes students don't do that; they just jump right into the questions. And that doesn't, then you're losing marks. So you're just defining what your variables are, right? We can go through each one too, right? We have VPA, which is the velocity of the plane relative to the air, and the velocity of the air relative to the ground. So you'd actually have 3 sentences here defining each variable. But I'm only going to write one on my screen. questions with that? This is a different way of doing things, as like everything else in our course. Physics is always different. Eric?
What would VPA be relative to that?
VPA is the velocity of the plane relative to the air. So that's usually your, like it, in your questions, it's how, if I generalize it, usually what you're going to see is you have the velocity of an object to your medium. Then the next one is the velocity of the medium to the earth. And then your resultant vector is usually the object of the object to the earth. Right? So your objects, for most of our cases, are either going to be boats or planes. Your mediums are going to be air or water. And your earth is always the earth, or ground or shore, depends on the situation. So when you see the first one up there, PA, that's how fast your plane can go based on its engine power. Right, if it was no wind that day, that's its air speed. Sometimes it said like air speed, or if it's a boat, it usually says like the boat speed on a calm day or in a pool, something like that. So there'd be no wind or current. Does that make sense? Okay. Any other questions with this slide? Okay. Yeah, and I put this slide up here. You don't have to write it down. Just to remind you again that X and Y are independent of each other. So whatever happens in the X doesn't impact the Y per se. So in this case here, let me erase what I have. In this case here, you have the velocity of this boat relative to the water. We have the velocity of the water relative to the shore, and the velocity of the boat relative to the shore. So when you're looking at a triangle, the across the river arrow is dictating how fast they get to the other side. Okay, so the time that it takes them to get over here has no impact on the current. If they point their boat directly to the other shore, or if there's no current, it might take 5 seconds to get across. If there's a strong current and they're still just pointing directly at the other shore, it's still going to take 5 seconds to get across. What's going to be different is that the stronger the current is, it's going to dictate how far down the river they get in that 5 seconds. Right? But the arrow that points from one side to the other is the only factor that figures out how fast you get across this river here. Right? So your X and your Y, because they're vectors, don't impact each other. I have 3 videos here. Oh, that one disappeared. That's too bad. The video that disappeared there, I'm going to see if I can find it again. It had some students in it, not from our school, showing relative motion, because I know some of you might choose the video option for your project. So it was a good example of what that looks like. The one up here, you can choose to watch it. I think it's like half an hour. And you can see it's made in 1960, so it's like over 50 years old. But it's made at Western University, and it still is a pretty popular clip to show what frames of reference actually is. So using 1960 technology, they show what frames of reference looks like using cameras. A frame of reference is a good, like, if you think of like viewing through your phone, if you're recording something, that's a frame of reference, and that's kind of how you should see the world. And this fear factor one, I just want to get to the math, so we'll come back to this if we have time. This was a show, I don't know if it's still on, I don't think it is, but it was like popular like 20 years ago. And sometimes I've seen revivals of it, where the contestants do things that are against their fears. And in this episode, the contestants had to jump from one transport truck to another one, separated by like 6 feet, as they traveled down the highway at 80 kilometers an hour.
That's enough for me.
So when you're doing that in our physics world without air resistance, it's not a hard thing to do, because the contestants who don't understand relative velocity, which is very few and far between, would think that they would have to jump forward when they leave their truck to get to the other one. because they have to account for the movements of the truck down the highway. But in reality, when they already have the velocity of the two trucks because they're going at the same speed, so they could just jump from one to the other in a very simple manner to get to the other side. It's not as hard as it seems. Because again, relative to the trucks, if you're standing on one truck, if both trucks are going at the same speed, right? Both trucks are going, because they're going both the same speed, one relative to the other is not moving anywhere. It'd be no different than jumping from one desk to the other. But it looks scarier because the trucks are moving really fast. So we can go back, as I said, go back and watch that if we have time. If we take a look at this animation, there you guys saw this last year? Yeah, so there you go. Right? Which of these two boats has the greater average velocity, the top or the bottom? Eric?
The top.
The top one, why does it have a higher velocity? Yeah, because it has the larger displacement, right? Because it's going on the hypotenuse there. Which one gets to the other side of the shore faster? Like crosses the river the quickest? What do you guys think? Alex?
Neither of them, they get there at the same time.
Yeah, so they get there at the same time because their x speed or the speed across the river is the same. So we take a look at this scenario here, Jake crossing the river. We'll look at this one and then there's one more here too. Have any of you gone to this beach? I forget where it is. It's in the Caribbean. I forget where it is. But the airport's like right beside the beach. And one of the fun things that people who make poor choices in life, they like to stand right at the end of the runway and get blown backwards by the jet engines as it flies over the top.
Isn't that hot air?
To me, it would be it'd be loud, so that'd be a problem, but also all the sand that gets blasted off the runway at you probably doesn't feel very good. People do it.
For fun?
But we can take a look at that in a second. So let's take a look at this problem here.
People are actually tripping.
So you can read the problem just as well as I can. And what the first question is that we have to figure out how he has to angle his body in the river so he goes directly to the other shore. And then part B is what is his speed according to how he's swimming. So take a second, read it, sketch it out, define your variables, and we'll do this together.
So he wants to.
Okay, so we have our three vectors here, right? Our three vectors are, we'll start with defining them. We have the velocity of Jake relative to the water. And what's the swimming speed tank? Okay, so that's the first one. The next one would be the velocity of the water relative to the shore. Which is also known as the current. That's going 5. So if you write it all in one line, you can use the ditto marks or quotation marks, which just means the same as the row above. I don't know if you knew that. The last one is the velocity of the water to the shore, or sorry, Jake to the shore. So we know Jake's going north. That's the direction that he wants to go in the problem. We know he has to angle northeast-ish to get, or north. Does he have to go northeast? No, he has to go northwest, right? Because he has to go into the current to counteract it. Well, I had that wrong. Right, so whatever Jake's going west has to go in counteract the east. So we have those three variables. So the next part, as always, is to draw a diagram. So if we draw the diagram for this one, right, so here's the shore on one side, shore on the other. Jake wants to go this way, straight across. So that's the velocity of Jake relative to the shore, right? And then we have two options for the triangles. We could do the blue triangle here, which is V, W shore, V, or we have the red triangle, which of those two triangles are correct? Jackson?
Blue.
No.
Red.
No, it's the red one, right? Because the water's going east, right? So that means that it's got, actually no, sorry, I take that back. You are right. Right? Blue is right, because the water's going east, so Jake has to go west. Sorry, I got my east and west mixed up. Right, so the red one's not right, but sometimes I see that on a test as the red one because students get into the mindset of always using the velocity of the object relative to the shore as a hypotenuse. So it is the blue one. Let's get rid of the red one. So that's 90 degrees in there. So question A is to find that angle in there, right? So we know the hypotenuse and we know the one of the legs. And
The 90 degree is the other corner, it's not like the one.
you're 100% right. There we go. Sorry. So now that I have it right, 2 mistakes in 2 minutes there. We want to find theta, so the direction. How do we find the direction? It's a right angle triangle. We know 2 sides. How are we going to find theta? Jake, how are we going to find theta?
The tangent of the x component over the y component.
The tangent? No, that's a hypotenuse down here.
Or no, like break it into the.
Pardon? We know this and we know this, right?
Oh, right. So you did the sign of the water with the.
Yeah. Yeah. So theta works out to be 30 degrees. You notice I didn't convert to meters per second because it is just a ratio. The units cancel out anyways. All right, so in your therefore statement, you'd say like, therefore Jake has to point his body north 30 degrees west to make it directly across the other shore. And B, how do we find his speed relative to the shore? All right, so the speed relative to somebody on the shore. Jake, right back at you. What are you going to do? How do you find this missing side of your triangle?
You can use either cosine or tangent in my water speed or shore speed.
That is not the best way. That is a way, but you should always try to use the number that are given to you in the question. We're not going to use sine or cosine or tan. Andre?
Pythagorean theorem?
Never use the Pythagorean theorem because it uses the numbers that were given in your question. Just in case you left your calculated radian mode so that answer is wrong, then that way you won't get it wrong. Second one wrong. So what do we have? We have V JW squared equals B WS squared. So Jake's speed across the water is actually slower than the speed that he's swimming because he has to use some of his energy to counteract the current.
In the first part, why is Jake's speed relative to the water not, why is it the hypotenuse and not just like A or C, or B, sorry?
Because if he wants to swim to a location directly north of the starting point. So he wants to go directly north.
So would there be a problem with calculating first the angle of the tangent between 10 and 5, like this, and then this angle here, and then that angle would have to be as offset, and then from that you create a new triangle, and then you calculate the hypotenuse of that triangle?
As long as you get 30 degrees your way, then sure.
Okay. I didn't get 30 degrees, but I got the 8.66. It's like the tangent, the inverse tangent of 5 over 10.
Did you get 60?
It's like 26.
That's not right.
You have an obsession with making multiple triangles.
I do.
You have done it for every single thing we've learned. You made multiple triangles.
Okay, so we're good? Any questions with that one? So you have to take time to think about how the vectors go, right? Put them together in the right way, and then we get our answer right here. Eric.
On a test, do we have to write it in like those type of sentences?
You do. You do. Because you have to define each of the variables, right? It goes back to that they're all velocities. So if you just call it V1, V2, V3, right? Only in the topic of a relative velocity are there two subscripts because you have to say it helps describe what's relative to what, right? I think there might be a question in your homework where it's like, there's a person on a cruise ship that's walking towards one side of the boat. The current in the water is pushing the boat. What is the velocity of the person relative to the shore? So it actually has 4 vectors, like for relative motion. So you got to add all 4 together, and however the question puts it together, right? So you got to have all your letters line up and know what they are.
And what do those quotes mean?
Quotes just mean same as above. It's an old, like it's shorthand, so you don't have to keep on writing the same thing. They're called ditto marks. It's a way of taking notes. Andre?
Do you only need to do these sentences for these types of questions, not for the other ways of solving we learned before?
Anything that deals with relative motion, you have to do this. That's the only time all year that you have to do it.
But not projectile?
No, because you're not gonna, because I already know what delta dy is,
Okay.
right? So it's when you have, if you have 4 delta dy's, then you'd have to kind of explain what each one means. Right, in this case, it just takes a little bit more. All right, so if we take a look at this one, Maddie's not here today. But this uses components along with this, put everything together to get the answer. So I'll let you guys can do this one on your own. Good luck. I'll come around and help you out if you need it. But you have two vectors and you're just trying to find the third, right? And matching up with the answer up here. And you know it works out because the answer is yes.
Any other questions?
Not to choosing not to do it. I'm just thinking about it in my head for the.
The last one, the 71.
That's like the answer.
Oh, that's good. Yeah. Oh, so that's the thing relative to.
Yep.
Yep.
Brian, are you okay? You guys okay here? Yep. We can throw the air. Very good.
This is the correct picture, right?
So yeah, we have your plane, the airspeed of the plane's 230 north, whatever east. The other one is west south, so you have it northeast, you have the west south. And then the ground speed.
And I can see It's really messy. I know you can.
Northeast, and then the next vector goes southwest, right?
It's the most difficult thing to understand because it's very small.
Yeah, from the end of the other one, though, right?
That's correct.
It's
basically this.
So in the west and the south.
Yep.
Okay.
Yep. You guys okay? Make sure when you guys are doing this one too, you don't like deceive yourself, right? Your first vector, as I walk around there, I see some of you, like not everybody has the same picture. So when you guys have the picture, there's my camera here. When you have the picture for this one, the first vector, right, is northeast, like 230 northeast. Right, so go somewhere in that direction. So that would be your velocity of the plane relative to the air goes that way. Right, your second one, which is the wind, is going southwest, and it's what, like a third long of the other one, so it goes kind of like this. Right, the velocity of the air relative to the ground. Something like that. So your resultant speed then would be the vector that's in there, which I'll draw in green. Right, so if you draw your arrows out of proportion, you'll get a weird looking answer because, you know, based on this, the answer should be northeast. So if you draw that wind too long, it's going to look like it's going northwest. And just, there is homework too, just on the next slide. And I'll flip it quick on it.
Which is the?
Oh, yes. The component method, since we don't have any right angle triangle, like we don't have a right angle triangle like we did with the last lecture.
There we go. We have, sorry, you have to use component method. Each vector breaks itself into components to be right angle triangles. Yes. Yep. Yours, Doctor?
these are right angle triangles this time. So if you break each one into components, like north, south, east, west components, and have it together like your displacement question is this. All right, so this one looks like your displacement question on the quiz today, right? Just instead of displacement, we have velocity. Do you have the diagram? So the next step is to take your mean diagram here and break each of the vectors into components. So your north south component, your east west component. Just like in our quiz today, right? You took your displacement vectors and broke them down into east, west, and south. And that, and then you add the components together. It's the exact same process, just the very instead of displacement, I have the relative movement. Yeah. You have the next.
I'm confused. Why is the second vector drawn like that? I think the second vector is like confusing.
It's AG, right? Because the second vector, AG, is the air relative to the ground. Right? And it's going west 25 degrees south. Right, so that's why it's going